experiment that was done to kind of show what's happening with waves. So here, this is like, say an object that's producing a wave. It could be like two speakers, okay, producing waves. And these waves will actually interact with each other. Now, these waves aren't drawn like up and down, but one of these lines, so this line here, the first one, that's a trough, okay? Or I mean a peak. So anything with a solid, that's a peak or crest. So you should be writing and following along. And anything with the dotted line, okay, is a trough. Okay, I'm going to do the same on this one. And then I'm going to show you something. So now look here. Everywhere where there's a trough and a trough interacting, what's going to happen? It's going to get bigger, right? Or where there's a crest and a crest interacting, it's going to get bigger. That's going to be constructive interference, okay? But where, say, right here, this is the trough of this wave, and this is the crest of this wave. What's going to happen at that point? Oopsies. Oh, crap. Well, you know what I mean. Like at a point, say, where the crest and the trough of different waves are interacting, what happens there? Cancel out. It's destructive interference. So, I know it's hard to visualize. I'm sorry that my picture, here we go. And there, okay? So at each point where the blue and the black interact will be destructive. Every point where colors that are matching interact will be constructive. So I'll show you a little video. This guy is weird, but it really shows the video very well. Okay. It's a cartoon.
First need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
you know particles will behave a certain way and waves behave a certain way, what will electrons do? What do electrons behave as? Do they behave as particles or as waves? Don't remember? Who thinks waves? Who thinks particles? You're all wrong. Electrons act like both. They have both particle properties and wave-like properties. Electrons act like waves, but we have to think about them as particles as well because they also behave as particles. And this was a famous experiment to show us that electrons must act like waves because of what we see with this experiment.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other.
Anyways, okay. Also, this was I've shown this one to you before, but this is a really good website for what we're doing today, physicsclassroom.com, and if you go to, they have, so right now we're doing lesson 3 on waves, behavior waves, interference. And it basically goes through everything that we did today, constructive, destructive, and principle of superposition. So, and then there's, well, there's only one question for this one. Oh, no, there's 2, okay? And then there's questions at the end to kind of help you. So this is basically, this was our entire lesson today. So that might be a good thing to just review, just read over to help you out. Also, there's one on Khan Academy that's exactly what we did today, and you could just type in Khan Academy wave interference, and it's a 15-minute video that goes through it. I actually want to show you like the first minute. So,
if two waves overlap in the same medium, we say that there's wave interference. So this box here could represent a speaker, and this could be the sound wave it generates. Or it could represent a laser, and this would be the light wave it generates. Or it could be some sort of ripple tank generator, and this is the water wave it generates. Regardless, if you had a second source of a wave, and these were to overlap and cause wave interference, and what that would look like would be something like this. So let's say these are speakers. I like thinking about it in terms of speakers. I think it's easy to think about. And I put this speaker right next to the first speaker, side by side. So they'd be creating sound waves in this region. And I wouldn't really have 2 sound waves necessarily. You could think of it as just having one total sound wave. And how would we find the size of that total sound wave? Well, if I put an axis in here, the axis will make it easier for me to think about this. I'm going to put an axis through here like this. What I can do is I can just ask myself this. I'm going to say, what was the value of the first wave? So I'm going to take that value. What was the value of the second wave? And I'm just going to add them up. To get the value of the total wave, I'd take that value of the first wave plus the value of the second wave, and, well, I just get double in this case. And I can come over to here, okay, value here plus the value there. I get double that point. It's not going to be as high because they weren't as high. And then over here I got 0 and 0 is just 0, and you start to see what's happening. You can come down here. very low or very negative, and I get double that down here. And if I were to trace this out, what I get is one big total sound wave that would look like this. So these have been amplified. So that's one possibility. When two waves overlap,
Okay, so you get the idea. It basically goes through very similar examples, but if you need a little bit of extra help, go on there. Also, this is another really good one, windows2universe.org, and this was what I talked about with wave beats. And then it actually starts talking about, you could go and read about the Doppler effect, is what we're going to do in a couple of minutes too. So, anyways, those are some to jot down to help you out.